Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Look up at the night sky. That pale sentinel watching over Earth for 4.5 billion years, our moon, has shaped life on our planet in ways most of us rarely consider. But what if, through some cosmic impossibility, our moon simply vanished? Not gradually drifting away as it naturally does at a rate of 3.8 centimeters per year, but instantly, there one moment and gone the next. The consequences would be far more catastrophic than most people realize. Tonight, we're exploring a thought experiment that reveals the moon's crucial role in Earth's delicate balance. This isn't about myths or superstitions. This is about hard physics, planetary science, and evolutionary biology colliding in a scenario that would fundamentally reshape our world. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The moon's relationship with Earth began approximately 4.5 billion years ago when a Mars-sized object called Theia collided with early Earth. The debris from this cataclysmic impact coalesced to form our lunar companion. Since then, the moon has been Earth's constant companion, its gravitational influence quietly orchestrating numerous systems we take for granted. If the moon suddenly disappeared, the first noticeable effect would occur immediately in our oceans. The moon's gravitational pull is the primary driver of Earth's tides, responsible for approximately 2/3 of tidal forces, with the sun generating the remaining third. Within minutes of the moon's disappearance, tidal patterns worldwide would begin to change dramatically. Coastal regions would witness tides dropping to roughly 1/3 of their normal range. Ports and harbors designed around predictable tidal schedules would face immediate disruption. Vessels caught in rapidly changing currents might struggle to navigate safely to shore. But this initial disruption represents just the beginning. Marine ecosystems evolved over millions of years in harmony with lunar-driven tidal patterns. Intertidal zones, those unique environments that transition between sea and land with each tidal cycle, would permanently shrink. Countless species that time their breeding, feeding, and migration patterns to tidal rhythms would face immediate stress. Consider the grunion, small fish that time their spawning precisely to spring high tides, or horseshoe crabs, whose ancient reproductive cycle depends on the highest tides during full and new moons. These and countless other species would need to rapidly adapt or face potential extinction. Beyond tides, the moon stabilizes Earth's axial tilt. Currently, our planet tilts at approximately 23.5 degrees relative to our orbital plane around the sun. This tilt gives us our seasons, but without the moon's gravitational anchoring, Earth's tilt would begin to wobble chaotically. Over time, potentially swinging between 0 and as much as 45 degrees, such axial instability wouldn't manifest immediately. It would develop over thousands of years. But once established, these wild variations would create extreme seasonal changes that would render many regions uninhabitable. Areas that once had mild, predictable climate patterns could swing between scorching heat and bitter cold within a single year. As the first night of the moon's absence falls, astronomers worldwide would document another startling change. Our night skies would grow dramatically darker. Without lunar reflection, nights would be illuminated solely by starlight and artificial lighting. This darkness would affect more than human visibility. It would disrupt nocturnal animals that evolved to navigate by moonlight and potentially alter predator-prey dynamics across numerous ecosystems. The loss of our celestial neighbor would mark the beginning of profound changes to Earth's systems, changes that would unfold across timescales ranging from minutes to millennia. And as we'll discover in the next segment, the moon's disappearance would also trigger surprising consequences for Earth's rotation and our measurement of time itself. The moon doesn't just light our night sky and drive our tides, it fundamentally controls Earth's rotation. Currently, Earth completes one rotation in approximately 24 hours. However, this wasn't always the case. Fossil records and geological evidence suggest that during the dinosaur era, roughly 70 million years ago, Earth rotated faster, with days lasting only 23 hours. This gradual slowing of Earth's rotation occurs because the Moon exerts tidal friction on our planet. As Earth rotates, the tidal bulges created by lunar gravity act like brakes, gradually transferring Earth's rotational energy to the Moon, causing our days to lengthen by about 1.7 milliseconds per century. If the Moon suddenly vanished, this braking mechanism would disappear. Earth's rotation wouldn't immediately accelerate, but over thousands of years, other factors, including the Sun's gravitational effects and Earth's internal mass distribution, would begin to alter our planet's rotational behavior unpredictably. Computer. Models suggest Earth's rotation would likely accelerate slightly and become increasingly unstable. Without the Moon's stabilizing influence, our planet could develop precession wobbles, similar to what we observe in Mars, whose two tiny moons provide minimal stabilizing effect. Dr. Mattia Chuk from the SETI Institute explains, "The Moon acts like a gyroscopic stabilizer for Earth. Remove that stabilizer, and Earth's axial tilt would eventually experience chaotic variations with profound implications for climate patterns worldwide. These rotational changes would eventually necessitate a complete recalibration of how we measure time. Our current 24-hour day, divided into hours, minutes, and seconds, would gradually become misaligned with the actual rotational period. Timekeeping systems worldwide would require continuous adjustments. Beyond timekeeping, consider agriculture, i.e., fundamental human activity meticulously synchronized with seasonal patterns. Modern agricultural practices depend on relatively predictable seasons, which exist because Earth's axial tilt remains stable around 23.5 degrees. Without the Moon's stabilizing presence, these seasonal patterns would gradually become erratic. Initially, farmers might notice subtle shifts in growing seasons. Over centuries, these changes would intensify. Regions once ideal for certain crops would become unsuitable, as seasonal temperature variations became extreme and unpredictable. Global food security would face unprecedented challenges as agricultural zones shifted unpredictably. The Moon also influences animal behavior and reproduction through its regular cycles. Many species time their breeding with lunar phases. Corals across the Great Barrier Reef, for instance, simultaneously release their reproductive cells based on lunar cycles, water temperature, and day length. Without lunar cues, they're synchronized. Spawning would be disrupted, potentially affecting reproduction success. Similarly, numerous bird species use moonlight for navigation during migration. The disappearance of the Moon would force rapid evolutionary adaptations in navigational strategies. Some species might successfully adapt. Others would likely face population declines or extinction. Perhaps most concerning for modern human society would be the effect on satellite communications. Currently, engineers design satellite orbits accounting for both Earth's and the Moon's gravitational fields. The sudden absence of lunar gravity would alter the orbital dynamics of every satellite circling Earth. Low Earth orbit satellites, including those providing internet services, weather monitoring, and Earth observation, would experience orbital perturbations. Without course corrections, many would eventually decay into unstable trajectories. Our interconnected global infrastructure could face significant disruption, as satellites require extensive repositioning. Meanwhile, on Earth's surface, geologists would detect subtle but increasingly significant changes in crustal movement. The Moon's gravitational pull influences Earth's lithosphere, contributing to tectonic plate movement. While the immediate effects would be minimal, over decades, seismic activity patterns could shift as tectonic plates respond to the altered gravitational environment. As Earth's rotation and axial stability gradually changed, one of the most profound, long-term consequences would emerge: the destabilization of our climate system. The Moon helps maintain Earth's climate by stabilizing our axial tilt within a narrow range that supports life as we know it. Without this celestial stabilizer, our Planet would begin a journey toward climate chaos, unlike anything experienced in human history. The Moon's gravitational influence extends far beyond tides and rotation. It fundamentally anchors Earth's climate system. Our planet's axial tilt of 23.5 degrees remains relatively stable thanks to lunar gravity. This stability has allowed complex ecosystems to evolve and thrive within predictable climate patterns for millions of years. Without the Moon, computer simulations indicate Earth's axial tilt would begin fluctuating dramatically over periods of tens of thousands of years. These fluctuations could range from near 0 degrees to potentially over 40 degrees. For comparison, Mars, which lacks a large stabilizing moon, has experienced axial tilt variations between 15 and 45 degrees over its history. Dr. Jacques Lascar of the Paris Observatory, whose team has conducted extensive modeling of planetary axial dynamics, explains, Earth without the Moon would experience chaotic obliquity variations that would fundamentally reshape climate zones repeatedly over geological timescales. At lower axial tilts approaching 0 degrees, seasonal differences would diminish globally. Equatorial regions would receive consistent, intense solar radiation year-round, while polar regions would remain perpetually cold with minimal seasonal variation. This would trigger massive redistribution of heat through atmospheric and oceanic circulation systems. Conversely, at extreme high tilts of 40+ degrees, seasons would become severe beyond anything in human experience. Regions currently experiencing mild seasonal variations would face scorching summers when tilted toward the sun and brutally cold winters when tilted away. These extremes would stress plant and animal life adapted to current conditions. The climate consequences would unfold gradually but inexorably. Initially, subtle shifts in seasonal patterns might manifest within decades. Over centuries, more pronounced climate zone shifts would occur. Within thousands of years, Earth's climate would bear little resemblance to the stable patterns that allowed human civilization to develop. These changes would drastically alter precipitation patterns worldwide. The Intertropical Convergence Zone, AE, critical rainfall band near the equator, would shift unpredictably as Earth's axial tilt varied. Regions currently receiving reliable monsoon rainfall might experience extended droughts, while historically arid areas could see unprecedented flooding. Ocean circulation patterns would undergo equally dramatic transformations. The thermohaline circulation, often called the global ocean conveyor belt, distributes heat worldwide and influences climate across continents. This system depends partially on the stable relationship between land masses and ocean basins, maintained by our current axial orientation. As Earth's tilt became more extreme and variable, altered wind patterns and temperature gradients would disrupt ocean currents. The Gulf Stream, which keeps Western Europe much warmer than its latitude would suggest, could weaken or relocate. Similar changes would affect currents like the Kuroshio in the Pacific and the Agulhas around southern Africa. Polar ice caps would experience particularly dramatic changes. During periods of extreme tilt, polar regions would receive intense summer sunlight at low angles for months continuously, potentially accelerating ice melt beyond anything currently projected in climate models. Conversely, during winter, these same regions would experience months of continuous darkness and extreme cold. The resulting sea level fluctuations would exceed anything in human history. Coastal cities worldwide would face existential threats. As shorelines advanced and retreated over cycles of thousands of years, human infrastructure, built during Earth's stable Holocene period, would prove increasingly maladapted to these new climate realities. Ecosystem boundaries would shift dramatically and unpredictably. Biomes that evolved within specific climate envelopes, tropical rainforests, temperate deciduous forests, grasslands, and tundra would face conditions outside their evolutionary experience. Mass migrations of plant and animal species would occur, limited by natural and human-made barriers. For agriculture, these changes would necessitate continuous adaptation. Crop varieties developed for specific growing conditions would become increasingly unsuitable for their traditional regions. Agricultural productivity would likely decline during transitional periods as farmers and agricultural scientists raced to develop varieties adapted to changing conditions. The psychological impact on human societies shouldn't be underestimated. Humans evolved under relatively stable climate conditions, with predictable celestial patterns. The moon has been a constant companion throughout human existence, influencing art, religion, timekeeping, and navigation across cultures. Its absence, coupled with increasingly erratic seasons, would profoundly challenge human psychological adaptation. As these climate transformations accelerated, another equally significant change would be unfolding in Earth's oceans, a transformation that would reshape marine ecosystems and potentially alter the course of evolution itself. The sudden disappearance of the moon would trigger a cascade of changes in Earth's oceans that would reshape marine ecosystems from surface to seafloor. The most immediate and visible change would be the dramatic reduction in tidal range as lunar gravitational forces vanished, leaving only the sun's weaker tidal influence. Tidal zones, those unique transitional environments between land and sea, would contract significantly. These zones host remarkably diverse ecosystems adapted to the rhythmic flooding and exposure created by lunar tides. Organisms ranging from barnacles and mussels to specialized algae and predatory sea stars have evolved precise adaptations to specific tidal heights. Dr. Helen Gurney-Smith, marine ecologist at the Fisheries and Oceans Canada, notes, "Intertidal organisms are exquisitely adapted to precise positions within the tidal range. A radical reduction in tidal amplitude would create immediate ecological pressure, forcing rapid adaptation or local extinction for many species. Particularly vulnerable would be coastal wetlands, salt marshes, mangroves, and tidal flats that depend on regular tidal inundation. These environments serve as crucial nurseries for commercially important fish species and provide essential ecosystem services, including carbon sequestration, shoreline protection, and water filtration. With reduced tidal flushing, many of these areas would either become permanently submerged or permanently exposed. Either outcome would fundamentally alter their ecological function. The transition would likely see significant die-offs before new ecosystem equilibriums could establish. Beyond coastal regions, the open ocean would experience equally profound changes. Many marine species synchronize their reproductive cycles with lunar phases. Corals across tropical reefs worldwide simultaneously release gametes based on specific combinations of lunar phase, water temperature, and day length, a spectacular phenomenon called mass spawning. Without lunar cues, this reproductive synchronization would fail. For species that evolved to maximize reproductive success through synchronized spawning, this could significantly reduce population viability. Over generations, selection pressure would favor individuals less dependent on lunar cues or able to utilize alternative environmental signals. Ocean circulation patterns would also begin shifting as the combined effects of altered tides and gradually changing Earth rotation modified how energy transfers between the atmosphere and ocean surface. These circulations distribute nutrients, heat, and dissolved gases throughout the marine environment. Upwelling regions, areas where nutrient-rich, deep waters rise to the sunlit surface, are particularly important for marine productivity. These regions support some of the world's most productive fisheries. Changes to circulation patterns could relocate or diminish these upwelling zones, with significant consequences for marine food webs and human food security. The loss of strong tidal mixing would also affect ocean stratification, the layering of water masses with different temperatures and densities. Enhanced stratification could reduce nutrient exchange between deep and surface waters in many regions, potentially decreasing primary productivity by phytoplankton, the microscopic organisms that form the base of marine food webs. Marine migrations would face disruption as well. Many species, from tiny planktonic organisms to large whales, time their movements according to lunar-influenced factors. For instance, certain zooplankton perform daily vertical migrations based partly on light conditions, including moonlight. These migrations represent the largest animal movement on Earth by biomass and are crucial for nutrient cycling and carbon sequestration. Meanwhile, across the abyssal plains of the deep ocean floor, communities around hydrothermal vents and cold seeps might seem isolated from lunar influence. However, even these extreme environments would eventually experience changes as altered tidal forces modified pressure gradients, influencing fluid flow through seafloor geological systems. For humans, the consequences would extend beyond ecological considerations. Coastal infrastructure designed around historical tidal patterns would become increasingly maladapted. Ports constructed with specific tidal ranges in mind would face operational challenges. Tidal power generation facilities would become obsolete almost immediately. Maritime navigation would require comprehensive revision as tidal current predictions, vital for safe passage through many coastal waters, would no longer apply. Shipping routes and schedules worldwide would need recalculation to adapt to new oceanographic conditions. Perhaps most concerning for coastal communities would be changes to storm surge patterns. While tides would decrease, the complex interaction between reduced tidal forces, altered Earth rotation, and gradually shifting climate patterns could actually increase vulnerability to coastal flooding during extreme weather events in some regions. As marine ecosystems struggled to adapt to these oceanographic changes, terrestrial life would face its own challenges, particularly organisms that evolved behaviors specifically tuned to the moon's rhythms and light. The night, once regularly illuminated by our celestial companion, would take on a new character with profound biological implications. The moon has been Earth's nighttime companion throughout the evolution of life, its predictable phases providing a rhythmic cadence of illumination that has shaped countless biological adaptations. Its abrupt disappearance would plunge our nights into a darkness that would profoundly affect behaviors across the tree of life. Without lunar illumination, nights would become approximately 30 times darker on average. During full moon phases, the moon currently provides approximately 0.1 lux of illumination at Earth's surface, enough for humans to navigate without artificial light and for many animals to conduct critical nighttime activities. Without this light source, nighttime would be illuminated solely by starlight and airglow, providing roughly 0.003 lux, functionally complete darkness for most visual systems. Dr. Teresa Schwartz, chronobiologist at the University of Vienna, explains, "Moonlight isn't just about visibility. It's a critical Zeitgeber or time cue that entrains biological rhythms across numerous species. Its absence would trigger behavioral and physiological disruptions we can barely predict. Among the most immediately affected would be nocturnal animals that rely on moonlight for hunting, foraging, navigation, or predator avoidance. Many prey species have evolved behaviors specifically timed to lunar phases, becoming less active during brightly lit full moons when predator detection increases. This delicate predator-prey balance would undergo rapid recalibration. Birds that migrate at night often use lunar orientation as part of their navigation strategy. Species like the indigo bunting or European robin calibrate their internal compasses, partly through lunar positions. Without the moon, these species would need to rely more heavily on stellar navigation, potentially reducing migration precision until adaptation occurred. Insects would experience equally significant disruptions. Many species time their reproduction precisely to lunar cycles. Pololo worms in the Pacific release their reproductive segments during specific moon phases, while female glowworms use their bioluminescence most effectively against the backdrop of particular lunar illumination levels. For plants, the consequences would be subtler but no less important. While photosynthesis primarily depends on sunlight, research has shown that moonlight influences plant developmental timing, defensive chemistry, and interactions with pollinators. Some species flower specifically during full moon periods when their nocturnal pollinators are most active. Perhaps surprisingly, the lunar cycle also influences coral reproduction worldwide. Corals across vast reef systems synchronize their spawning events using a combination of water temperature, day length, and critically, lunar phase. This synchronization maximizes reproductive success by saturating predators and ensuring genetic mixing. Without lunar cues, this spectacular coordinated event would become desynchronized. Marine organisms from zooplankton to sea turtles also time-critical behaviors to lunar illumination. The hatchlings of endangered sea turtle species use the moon's reflection on water to navigate from nesting beaches to the ocean. Without this guidance, hatchling mortality would likely increase significantly until behavioral adaptations emerged. For humans, the loss of moonlight would have complex repercussions. Anthropological evidence suggests that lunar cycles have influenced human behavior throughout our evolutionary history. Before artificial lighting, moonlight significantly extended productive human activity time each month, shaping work patterns, social gatherings, and cultural practices. More controversially, some research indicates potential relationships between lunar cycles and human physiology, including subtle effects on sleep quality and possibly reproductive timing. While many claimed lunar effects have been debunked, the complete absence of moonlight would provide an unprecedented natural experiment in human chronobiology. From a cultural perspective, the psychological impact would be profound. The moon appears in the mythologies, religions, art, literature, and calendrical systems of virtually every human culture throughout history. Its absence would create a sense of cosmic disruption, potentially triggering widespread existential anxiety and requiring significant cultural adaptation. Night sky observation would be forever altered. Amateur astronomers might appreciate the improved visibility of faint celestial objects previously washed out by lunar glare. However, the loss of our most accessible astronomical object, one that reveals features visible with the naked eye, and simple optical instruments, would remove a crucial gateway experience that has inspired countless people to explore astronomy. Beyond direct biological and cultural effects, darker nights would also impact human safety and security. Moonlight currently provides natural illumination for nighttime activities in regions with limited artificial lighting infrastructure. Its absence would increase dependence on artificial light sources, potentially exacerbating energy consumption and light pollution. As life on Earth adapted to permanently darker nights, other fundamental changes would be unfolding in our planet's protective shields. The moon's disappearance would initiate subtle but progressively significant alterations to Earth's magnetic field and atmosphere, systems critical for defending terrestrial life against cosmic threats. The relationship between Earth's magnetic field and the moon is subtle but significant. While the moon doesn't directly generate Earth's magnetosphere, its orbital mechanics and gravitational interactions influence our planet's rotation, which, in turn, affects the geodynamo, the self-sustaining process that generates Earth's magnetic field within our planet's liquid outer core. Earth's magnetic field serves as our primary defense against harmful solar and cosmic radiation. Without it, our atmosphere would be gradually stripped away by the solar wind, similar to what happened to Mars billions of years ago. The moon's stabilizing influence on Earth's rotation contributes to the relative stability of our magnetic field. Dr. Catherine Johnson, planetary scientist at the University of British Columbia, explains, Earth's magnetic field generation depends on complex fluid dynamics in the outer core, driven partly by our planet's rotation. Any significant change to rotational dynamics could eventually influence magnetic field behavior. If the moon disappeared, the resulting changes to Earth's rotation, including potential wobbles and altered spin rate, would eventually influence convection patterns in our liquid outer core. While these effects would manifest over centuries rather than immediately, they could potentially lead to more frequent magnetic pole reversals or periods of reduced magnetic field strength. During magnetic pole reversals, which naturally occur, every few 100,000 years, Earth's magnetic field doesn't vanish, but becomes temporarily weaker and more complex. These periods potentially expose Earth to increased cosmic radiation. Without the moon's stabilizing presence, such events might become more frequent or prolonged. Increased cosmic radiation reaching Earth's surface would have biological consequences, potentially including higher mutation rates in organisms and increased cancer risks for humans. Technology would also face challenges, as satellite electronics and power grids would require enhanced radiation protection. Beyond magnetic effects, Earth's atmosphere would experience its own set of changes following the Moon's disappearance. Lunar gravitational forces create subtle tides, not just in oceans but in our atmosphere as well. These atmospheric tides help drive certain wind patterns and influence energy distribution throughout the atmosphere. Without lunar atmospheric tides, circulation patterns in Earth's upper atmosphere would gradually reorganize. The thermosphere and ionosphere, upper atmospheric layers critical for radio wave propagation and satellite operations, would develop new dynamic patterns. These changes would necessitate adjustments to global communication systems and satellite operations. Perhaps surprisingly, the Moon's absence could eventually influence Earth's atmospheric composition itself. Current research suggests that lunar gravitational forces contribute to mixing processes that help maintain atmospheric gas distributions. Without this mixing influence, slight compositional stratification might gradually develop. Additionally, the previously discussed climate changes resulting from axial tilt variations would drive significant atmospheric adaptations. Altered temperature, gradients between equator and poles would modify global wind patterns, potentially shifting jet streams, storm tracks, and precipitation belts. Dr. Maya Kerlich, atmospheric physicist at the Max Planck Institute, notes, "The atmosphere represents a complex fluid system responding to numerous forcing mechanisms. Remove the Moon's gravitational influence, and you create cascading effects throughout this system that would manifest across multiple timescales. For weather forecasting, these atmospheric changes would create unprecedented challenges. Current meteorological models incorporate lunar gravitational effects on both oceans and atmosphere. Without these influences, new models would need development, and prediction accuracy might temporarily decrease during the adaptation period. The combined effects on magnetic field and atmosphere would also impact Earth's delicate relationship with space weather, the varying conditions in near-Earth space driven primarily by solar activity. Space weather events like coronal mass ejections can disrupt satellite operations, communication systems, and power grids when they interact with Earth's magnetosphere. With potentially altered magnetic field dynamics, Earth's vulnerability to extreme space weather events might gradually increase. Critical infrastructure, including electrical grids, satellite networks, and navigation systems, would require enhanced protection and redundancy measures. Beyond our magnetosphere, Earth's radiation belts, zones of energetic charged particles captured by our magnetic field, would undergo reconfiguration as field strength and geometry changed. These Van Allen radiation belts pose hazards to satellites and astronauts, requiring careful mission planning to minimize exposure. The space around Earth wouldn't be the only region experiencing change. The Moon currently serves as a natural shield, intercepting some incoming meteoroids that might otherwise reach Earth. While this protective effect is modest, its absence would slightly increase the frequency of meteoroid impacts on Earth over long timescales. Collectively, these changes to Earth's protective systems would unfold gradually, allowing for technological adaptation. However, they would represent significant challenges requiring international cooperation and resource allocation to develop new protective measures for both biological life and technological infrastructure. As Earth's protective shields underwent these transformations, humanity would face perhaps its greatest challenge yet: adapting our civilization to an increasingly unpredictable world while confronting profound questions about our cosmic place and purpose. The disappearance of the Moon would trigger a civilization-wide adaptive response, unlike any challenge humanity has faced. While the most catastrophic physical consequences would unfold over thousands of years, human societies would begin responding immediately to both actual changes and anticipated future transformations. In the short term, the first decades after the Moon's disappearance, scientific communities worldwide would mobilize unprecedented resources to monitor and predict developing changes. New Earth observation satellites would launch to track shifting ocean currents, atmospheric patterns, and rotation dynamics. International scientific cooperation would likely reach new heights as researchers work to understand our newly unstable planet. Dr. Elena Jimenez, director of the Global Planetary Dynamics Institute, describes this challenge. We would be attempting to model cascading changes across Earth systems with limited historical analogues. This would drive computational geoscience and climate modeling to entirely new levels of sophistication. Coastal communities would face immediate adaptation requirements as tidal patterns simplified but became less predictable during the transition period. Ports, harbors, and coastal infrastructure would require significant redesign. Communities historically protected by tidal barriers would need new flood defense strategies implemented rapidly. Agricultural systems would experience gradually increasing stress as seasonal patterns began shifting subtly. Initial adaptations would focus on diversifying crop varieties to increase resilience against growing climate variability. Seed banks would gain renewed importance as repositories of genetic diversity needed for agricultural adaptation. As decades stretched into centuries, more fundamental adaptations would become necessary. Human settlement patterns, historically concentrated along coastlines, would likely shift inland as sea level predictability decreased and formerly stable coastal regions experienced new vulnerabilities. Energy systems would require transformation as well. Tidal power generation would become obsolete immediately, while changing wind patterns would gradually alter optimal locations for wind energy development. Solar energy might become more important in regions experiencing reduced cloud cover due to atmospheric circulation changes. Transportation networks designed around historical weather patterns and sea levels would need continuous modification. Shipping lanes optimized for prevailing winds and currents would require regular recalculation. Aviation would adapt to changing jet stream positions and atmospheric turbulence patterns. Cultural adaptations would parallel these physical changes. Calendrical systems historically incorporating lunar cycles would require revision. Religious and cultural traditions tied to lunar phases would transform or develop new symbolic meanings. Night sky observation would focus increasingly on planets and stars, as astronomers adjusted to permanently moonless skies. Perhaps most profound would be the psychological adaptation required. The moon has been humanity's constant celestial companion, inspiring art, mythology, science, and philosophy across cultures and throughout history. Its absence would create what anthropologists might call a cosmic vacancy, an empty space in human cultural and psychological experience. Dr. Samuel Chen, cultural anthropologist at Oxford University, suggests the moon's absence would likely generate new mythologies explaining its disappearance and new cultural expressions addressing our altered cosmic environment. We might see this reflected across religion, art, literature, and popular culture for generations. Educational systems would adapt to teach coming generations about both the historical moon and the new planetary reality. Historical photographs and videos of the moon would become cultural treasures, records of a celestial body now experienced only through documentation rather than direct observation. As centuries passed and Earth's axial variations intensified, human civilization would face increasingly fundamental adaptation challenges. Agricultural regions would shift unpredictably, forcing migration and agricultural innovation. Climate engineering technologies might develop in attempts to artificially stabilize Earth's climate despite growing axial instability. Some futurists suggest that the moon's disappearance might accelerate humanity's development as a spacefaring civilization. The existential recognition of cosmic vulnerability could drive increased investment in space technology, asteroid defense systems, and potentially even planetary engineering capabilities. Dr. Amara Washington, astrobiologist and future studies researcher, notes, throughout evolutionary history, environmental pressure has driven adaptation and innovation. The moon's disappearance would create unprecedented pressure for technological advancement, specifically focused on planetary stability and protection. In this challenging future, international cooperation would become not just beneficial, but essential for civilization's continuity. The gradual planetary changes would affect all regions, transcending national boundaries and requiring coordinated global responses. New international institutions might develop specifically to manage Earth's transition to a moonless state. While the scientific community couldn't prevent the fundamental planetary changes following the Moon's disappearance, human adaptability and technological innovation would provide significant capacity to mitigate their most harmful effects. Our species' greatest strengths, scientific inquiry, technological creativity, and cooperative problem-solving, would face their ultimate test. The Moon's disappearance, while initially catastrophic in many ways, might ultimately drive humanity to develop capabilities and perspectives that would transform our relationship with our home planet and the cosmos beyond. Through this cosmic trial, we might emerge as a more resilient, technologically advanced, and perhaps even wiser species, inhabitants of a changed Earth, looking outward to the stars with new understanding of our cosmic fragility and responsibility. Perhaps the most profound legacy of our vanished satellite would be this: by losing the Moon, we might finally fully appreciate both its gifts to our planetary evolution and our own capacity to adapt to a universe of unexpected changes.